SAS demonstration summary counts. So we're going to start with the example that was shown in the PowerPoint slides, where I'm creating a data set called asthma, and I'm inputting just 4 observations with and 3 variables. I'm inputting a variable SES, standing for socioeconomic status, and it's a character variable. Then I'm inputting a variable asthma, also a character string, and then I'm inputting the variable count, which gives the count for each combination of SES level and asthma level. So this first line of data that we're reading in, we can interpret this that there are 40 subjects who were coded as having low socioeconomic status and having had asthma. In this second observation, we have 100 subjects who would have been coded as having low socioeconomic status and did not have asthma. 30 subjects who had high socioeconomic status and had asthma, and 130 subjects who had high socioeconomic status but did not have asthma. Then we can go ahead and do a proc-freq of this data, and we're going to have our table statement, SES star asthma, and then we're going to request 2 different statistics. We're going to request the chi-square option, and we're also going to request the option rel risk. And very importantly, we need this weight statement to tell SAS how we are weighting our data. And so what we're looking at is the relationship between asthma and SES, and we're making use of summary data instead of patient level data. So we're making use of summary counts. So let's take a look at the output here. Here is our table that looks very much like a typical frequency distribution table with the numbers in each of the cells. We have our percentages, row percentage, and column percentage, and we're dealing with 300 participants. Because we requested the chi-square statistic, we have the information that comes with the option of chi-square. We also have our Fisher's exact test. So based just on the chi-square and the Fisher's exact test, it does appear that there's some association between socioeconomic status and asthma. And then since we requested the option rel risk, we're also provided with a table that shows estimates of relative risk, and we have 3 different estimates that are provided for us. First of all, we're given the odds ratio. So in case control studies, the relative risk is not appropriate. We are going to want to compute the odds ratio as a measure of the association between exposure and disease, or the event of interest. So in this table, we see that our odds ratio equals 1.73. And this suggests that subjects with low socioeconomic status are 1.73 times as likely as subjects of high socioeconomic status to have asthma. Then we have our cohort column 1 risk, or relative risk, of 1.52. And this means that the risk of getting asthma among subjects with low socioeconomic status is 1.52 times the risk of getting asthma for subjects with high socioeconomic status. And then this last entry for cohort column 2 risk, which is equal to about 0.88, it is not the inverse of 1.52. What this relative risk means is that the risk of not getting asthma among subjects with low socioeconomic status is 0.88 times the risk of not getting asthma for subjects with high socioeconomic status. So you're going to want to be careful how you would interpret the column 2 risk. I would usually focus on interpreting the odds ratio and interpreting the relative risk from column 1 risk. And usually when I do the coding for the variable that I'm interested in, I usually do the coding so the risk group is 1, is coded as 1. So here we have 1 equals low because I'm concerned about participants with low socioeconomic status. And then the outcome variable, or the disease group, I usually have 1 equal yes for the disease, 2 equal no. So it is important that you get this coding right, otherwise when you come down to interpret your odds ratio and relative risk, you won't be able to interpret that correctly. Another type of measure you can use with ProcFreq, and again you could use this with ProcFreq if we were doing person level data too, is the option CMH. And CMH, for those of you who are doing a lot of epidemiology, computes the Cochran-Mantel-Hensel statistics, which test for the association between the row and column variables after adjusting for the remaining variables in a multi-way table. So if we had a table of race by SES by asthma, then we could look at the association of socioeconomic status and asthma after adjusting for race. I'm just going to show you the statistics that are generated with the CMH option when we just go with SES star asthma, because we don't have information for race in our data set asthma. So here's what the output looks like when we ask for the CMH option. And again, it's very similar to what we saw before when we asked for relative risk. We have the summary for the case control type of study with the odds ratio. We have the summary if your type of study was a cohort, so this would be relative risk, where we're looking at column 1 as the risk. And then we have the summary of relative risk, where we're looking at column 2 as our risk. And again, this is just another option that you can use in ProcFreq, whether your data are summary counts or whether your data is person level data. Now let's look at an example of a matched case control study. And I want you to notice here that I didn't use the word count to indicate summary counts. Here I called my weighting variable sum numbers. So again, count is not a special variable name. I could give my weighting variable any variable name that I want. So I'm inputting data, again, 4 observations. The first variable is called vCase. The second variable is called vCont for controls. And my weight variable is called sum numbers. So in this study, each case was matched to a control based on some possible confounding variables, such as age or gender or study site. So for this first observation, we have 100 pairs of subjects where the case used vitamins and the control used vitamins. We have 50 pairs of subjects where the case used vitamins but the control did not use vitamins. We had 90 pairs of subjects where the case did not use vitamins but the controls used vitamins, and 200 pairs of subjects where neither the case nor the control used vitamins. So case and control is going to be, imagine case is some kind of disease and control are participants who don't have that disease. So we're trying to look at the association of whether the proportion of cases who used vitamins is similar to the proportion of controls who used vitamins. And the option that we are going to use to look at whether these proportions are similar is the agree option. And the agree option is used for McNemar's test and also for a kappa statistic, which is a statistic of agreement. And I've indicated here in the comments how we can interpret the kappa statistic of what we call inter-rater agreement. So let's run this code and take a look at our output and then go from there in terms of our interpretation. So here we have our 2x2 table of case use of vitamins and control use of vitamins. And so here this number 440 indicates that we have 440 pairs of cases and controls. So looking at the results of McNemar's test, we have a highly significant p-value of 0.0007, which suggests that the proportion of cases using vitamins differs from the proportion of controls using vitamins. And if we go down and look at our simple kappa coefficient, 0.33 indicates fair agreement between the case use of vitamins and the control use of vitamins. And that's not surprising, because if our McNemar's test is very, very significant, that would suggest that the proportions differ between the cases and controls. And if they differ a lot, then you're not going to have very good agreement between the cases and controls. So you're not going to expect that the results of the McNemar test and the kappa statistic are going to agree. A very, very significant result with McNemar's test is going to indicate low agreement for the kappa coefficient. And so again, our kappa statistic ranges from 0 to 1. It's kind of similar to a correlation coefficient. So a kappa coefficient that ranges between 0.21 and 0.40 indicates fair inter-rater agreement, or agreement between the matched pairs. 0.81 to 1.00 is going to suggest very good agreement. So the kappa statistic is often used when we're interested in inter-rater agreement. For example, if you have two different raters looking at microscope slides, how well do they agree with each other? That would be the normal situation where you might be interested in calculating a kappa statistic. The last thing I want to show is the test for trend. And so again, we're dealing with summary data. And again, I want to point out that these options we're using in Proc-Freq with our summary count data are options that could be used if we had regular patient level data. So I'm creating a data set called pain, and I'm inputting the dose, and I'm inputting a character variable, whether or not the subject had an adverse reaction, and then I'm inputting the weight variable, which I'm calling here count. And I'm using the @@ to tell SAS to keep inputting these three variables over and over. This minimizes the number of lines in my card statement. Note here I've put this cards semicolon. This is actually the exact same as data lines. When SAS was first developed, they used a cards statement instead of a data lines statement. I guess kind of as a throwback to when we used cards to do computer programming, and I by accident put in the card statement instead of the data line statement here. So we're reading in these 5 observations for dose level and whether there was an adverse reaction or not. And then in the Proc-Freq, I'm requesting a trend option, which produces the Cochran Armitage test for trend, which is a 1 degree of freedom test. And I'm also requesting the chi-square option, which gives the Mantel-Hensel chi-square, which is also a test for trend. So let's run all this code and see what it looks like. So here, if we look at our output, we see our different dose levels going from 0, 1, 2, 3, 4, and whether or not the subject experienced an adverse reaction based on the dose level that they were given. And I want to point out that you should focus on the row percentages. So here, at dose level equals 0, only 18.75% of the subjects had an adverse reaction. So 6 out of the 32 subjects at dose level 0 had an adverse reaction. At dose level 1, 21% of the subjects had an adverse reaction. At dose level 2, 28% of the subjects had an adverse reaction. So again, I'm focusing on the row percentages here. And notice then at dose level 4, we have about 72% of the subjects who had an adverse reaction. 23 of the subjects out of 32. So if we look at these row percentages, we see that they appear to be increasing linearly. So what we're interested in with this test for trend is whether the proportion of patients who have adverse events or adverse side effects from the treatment increase as the dose of the treatment increases. So just eyeballing this data, it appears that we have a trend going on. And now if we look at our statistics, we're going to want to focus either on the Mantel-Haenszel chi-square, which is a 1 degree of freedom test, and we see that it's highly significant, less than 0.0001. So that's one test of trend, the Mantel-Haenszel chi-square. The other test of trend is the Cochran Armitage trend test. And again, we see that it's highly significant. Some statisticians believe that the Mantel-Haenszel chi-square test is not the best test to use since it tends to result in significant trends even for relatively minor changes in proportions. Of course, in this example, both the Mantel-Haenszel chi-square and the Cochran Armitage trend test resulted in highly significant p-values. So for this test for trend, we are testing the null hypothesis that there is no linear trend versus the alternative hypothesis that there is a linear trend in this data. And with a p-value less than 0.001, we are concluding that there is evidence of a linear trend between dose level and the proportion of respondents having adverse events. The thing I want to point out in this demonstration is that all of the tests that I have shown here using summary counts can also be done with Proc-Freq for patient-level data. This concludes the SAS demonstration on summary counts.